Good day everyone. Myself Vaidegi working as Assistant Professor in Sri Muthukumaran Institute of Technology, Mangadu. Today the video lecture is from the subject EC3452 Electromagnetic Fields for 4th semester ECE student. The topic is from the Unit 2 Electrostatics. The topics are we are going to study the important electrostatic concepts related to energy stored in electric fields governing field equations and the flow of electric current in conducting materials. These topics help us understand how electric charges interact with each other, how electric potential is distributed in space, and how electric current flows under the influence of an electric field. These principles are essential in analyzing electrical circuits, electromagnetic devices, and electronic systems. By understanding these concepts, we can bridge the gap between theoretical electrostatics and practical engineering applications such as resistors, capacitors, and transmission systems. First, we see what is electrostatic energy. Electrostatic energy is defined as the amount of work required to assemble a system of electric charges by bringing them from infinity to their final position in space. When charges are brought together against the electrostatic force of repulsion or attraction, work has to be done, and this work is stored in the form of electrostatic potential energy. For a system of point charges, this stored energy depends on the magnitude of the charges and the distance between them. This energy is not stored in the charges themselves but in the electric field created by the configuration of these charges. The stored electrostatic energy represents the potential of the system to perform electrical work when the charges are allowed to move. The total electrostatic energy is given by W is equal to 1 by 2 summation of 1 by 4 pi epsilon naught Qi Qj by Ri modulus of Ri minus Rj. Next we see about the electrostatic energy in the continuous charge distribution. In practical situations, we often deal with continuous charge distributions rather than discrete point charges. In such cases, the charges is represented in terms of volume charge density denoted by ρ as a function of position. The electrostatic energy in a continuous charge distribution is expressed in terms of the electric field intensity present in the region. The quantity equal to 1/2 of epsilon times the square of the electric field represents the electrostatic energy stored per unit volume. By integrating this energy and density over the entire region where the electric field exists, we can determine the total electrostatic energy stored in the system. Next, in that, we see about the energy density of electric field. The electrostatic energy stored in any region of space depends on the strength of the electric field present in that region. The energy density is defined as the energy stored per unit volume and is given by 1/2 epsilon naught multiplied by the square of the electric field intensity. This expansion indicates that regions having stronger electric fields store more energy compared to regions with weaker fields. The concept of energy density is extremely useful in analyzing capacitors and electromagnetic devices This expression indicates the regions having strong electric field and the fields store more energy compared to regions with weaker fields. The concept of energy density is extremely useful in analyzing capacitors and electromagnetic devices as it allows us to determine how energy is distributed within an electric field and how efficiently a system can store electrical energy. Next we see about the Poisson's equation. Poisson's equation is one of the fundamental equations in electrostatics that relates the electric potential to the charge distribution present within a region. It is expressed mathematically as the divergence of the gradient of potential equal to minus charge density divided by permittivity. This equation is applicable in regions where electric charges are present. It helps in determining how the electric potential varies with position due to the presence of charge distribution. Engineers use Poisson's equation to analyze electric field behavior in devices such as capacitors, semiconductor junctions, and insulation systems. Next we see about the Laplace equation. Laplace equation is a special case of Poisson's equation that applies to regions where there are no electric charges present. In this case, the charge density becomes zero and the equation reduces to the divergence of the gradient of potential equal to zero. Laplace equation is widely used in analyzing electric potential distribution in charge-free regions such as the space between capacitor plates or around conductors. Solving this equation helps in understanding how electric fields behave when influenced only by external boundary conditions rather than the internal charge sources. Next we see about the physical meaning under the boundary conditions. Both Poisson's and Laplace equations must be solved along with appropriate boundary conditions in order to obtain a unique solution for the electric potential. Boundary conditions define how the electric potential or electric field behaves at the interface between different materials or regions. In charged regions, Poisson's equation is used, where in charge-free regions, Laplace equation is applicable. At the interface of two different media, the electric potential remains continuous and the normal component of electric flux density must satisfy the required boundary conditions. These conditions ensure accurate determination of electric field distribution in practical systems. Next we see about the uniqueness theorem in electrostatics. The uniqueness theorem states that the solution to Poisson's or Laplace equation within a given region is unique if the boundary conditions are completely specified. This means that for a particular electrostatic problem, once the potential or electric field is defined at the boundaries, there exists only one possible solution that satisfies both the governing equation and the boundary conditions. Physically, this implies that the electrostatic potential and the electric field in a system are completely predictable. This theorem is very important in engineering analysis because it guarantees that the obtained solution accurately represents the physical behavior of the system. Next we see about the current density. The current density is defined as the amount of electric current flowing through a unit cross-sectional area of a conductor. It is represented by the vector quantity J and is expressed as the product of charge density and drift velocity of charge carriers. When an electric field is applied across a conductor, free electrons start moving in a specific direction, creating an electric current. Although the drift velocity of electrons is very small, the presence of a large amount of charge carriers results in a measurable electric current. Current density helps in understanding how electric current is distributed within a conducting material. Next we see about the Ohm's law in the point form. Ohm's law in differential or point form relates the current density to the electric field intensity within a conducting material. It is expressed as J equal to sigma E, where sigma represents the electrical conductivity of the material. The conductivity is a measure of how easily a material allows electric charges to flow through it. Materials with high conductivity such as metals allow current to pass easily, whereas insulating materials have very low conductivity. This linear relationship between current density and electric field forms the basis for analyzing conduction in electrical systems. Next we see about the practical example, that is current flow in a resistor. Consider a resistor having a certain length and cross-sectional area with a voltage applied across its ends. When a voltage is applied, an electric field is established across the resistor, causing the free electrons to move and produce an electric current. The magnitude of current flowing through the resistor depends on the conductivity of the material, the length of the resistor, and its cross-sectional area. A longer resistor offers more opposition to current flow, whereas a large cross-sectional area allows more current to pass through. This example clearly demonstrates how both geometry and material properties influence electrical conduction. Finally, we came to the summary of this lecture. To summarize, the electrostatic energy represents the work required to assemble a system of charges and is stored in the electric field. Poisson's and Laplace equations are the fundamental mathematical tools used to determine electric potential distribution in charged and charge-free regions respectively. The uniqueness theorem guarantees that electrostatic problems have definite and predictable solutions when boundary conditions are specified. Current density and Ohm's law describe how electric charges move in conducting materials under the influence of electric fields. Understanding these concepts provides a strong foundation for studying electromagnetic theory and designing practical electrical and electronic systems. I hope you all understood. Thank you.